Hello everyone. Today is an exciting day. It's Monday, Monday morning, and I'm working from home today. So I just wanted to record this video and kind of conclude Math 2Z03, and want to thank you guys for sticking with me thus far. Okay, cool. So just because of the length of this assignment, I have kind of like some previous work that I wrote out for you guys, and I wanted to just kind of review what I had already written down, explain it, and get to writing out I would say, I don't know, the questions generally get harder as you go through the assignment, so kind of focusing on the latter questions. So our first question, find the inverse Laplace transform, and we see, this little, let me zoom in really quickly, kind of past the intro right now. So you see, a denominator that's like that. You really don't have a Laplace transform that can do all of that at once, at least not yet. And so we're forced to do our partial fractions. This is s over s cubed. That's like if you take the largest ordered s in the numerator and denominator, that's what you'll get. And so to factor out something like that, you have your just a, and then your second term will be your bs plus c. So it has the s, and then you're doing the s squared in the second one. Okay, and at this point, I'm sure you guys know how to do partial fraction decomposition, and so you just sub in your certain values for s to solve and isolate for a, b, and c respectively. You plug those back in, and you use the corresponding inverse Laplace transforms. This one, we have just like the 1 over s minus a. This one, s over s squared plus s over s squared plus k squared. And then this one's just k over s squared plus k squared. And we know that we get sine and cos with k going in the inside of that function. And that was the answer that was submitted, and it is correct. So nothing too crazy, just have to be cautious of your simplification, and everything will turn out just fine. Moving on to question number 2. This one we have an IVP, and so you're taking the Laplace transform of the right-hand side and of the left-hand side. You can refer to your slides on how you get this and why you get it, but you basically just get, for your largest order, this could have been like this could have been like y cubed, or like the derivative cubed, and you'd have something like s cubed times y at s minus s squared times y at 0, and then minus s times y prime at 0, and da 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 da. In this case, we have s squared times y at s, and then we reduce a term in the s, and then we multiply by the first initial condition, reduce the term another time, and multiply by a term up in the initial condition. And then y at s is simply just multiplied by y at s. Y is just multiplied by y at s. And so then you are isolating for y at x. That's like what you're solving for. And you factor it out respectively where it is. Move these two functions over, and you'll get that. And you can submit that, and you'll get the right answer. Okay. These questions, I don't really bother to go in too much detail, because so long as you are listening / following along with the general steps, you'll get the right answer. Just be careful in the simplification. So as soon as you have a denominator for question number 3, something that cannot be factored as is, in terms of, like, you can factor it, but you'll get complex roots, you got to complete the square, because we've only ever worked with, in our slide decks, with real distinct roots. Sorry, real roots. We've worked with non-distinct roots before. But let me move the iPad real quickly. But yeah, so a cool little trick for completing the square really easily and consistently is you look at your term in the middle, and you're going to use this formula. I would write this down on your cheat sheet just because it helps. Or if you remember, we've covered this in like grade 9, grade 10, but or maybe even grade 8. But yeah, so you're using this formula, and you will plug in whatever value it is there. This is just, I put negative b over 2, but you could, this is just positive. So it's just b over 2 squared, the b being the coefficient attached to the s, or the middle term. You could have something similar like x squared minus b x plus a. And then, you're just using this term right here. You plug it in, and you'll get the value being 81, which is what you're taking apart from your lone value at the end. So I'm taking out 81, leaving the 100 on the outside, and now this is what I'm taking the inverse Laplace of. Okay, cool. So with that, I know there's a lot written down here, but just stick with me on this. So when you see something like this, okay, there's a few different ways to approach it. You could try and solve it like how he did in the slide deck, which is like factor out the 2, and hold on, I got give me a second. Okay, so this is the right one. Okay, yeah. So like you could factor out the 2 and try and work with it like that, as in like write this in a different color. So like 2 at s plus 5 over s minus 9 squared plus 100. And in this case, hold on a second, guys. This is question number 3, right? Yeah, okay, cool. Just because I have a little bit written down. Yeah, so the end goal here, generally when you have a question like this, is to always get it in a form similar to how it is on your formula sheet. So that way you can actually apply your inverse Laplace. Now in this case, we definitely can't do that here, but we could maneuver it such in a way that we can. So for example, and sorry, I didn't include the 5 over 2 here when I did this. So I could do something like that. So completely factoring out the 2, just so I have the s on top. And that's what I want. I want just the s on top, because we don't have any Laplace transforms with a coefficient attached in the numerator. And so we could either spread it apart into like 2s over s minus 9 squared plus 100, and the 5 is like added, so plus 5 over s minus 9 squared plus 100. Or we could, maneuver and work with it in one fraction and then spread it apart later. And then in this case, what I ended up doing here was just instantly off the get-go splitting it apart. That way I didn't have to factor anything out here. And so there's 2 ways to do it. I won't go into both of them, but if you want to try a different way of doing it, try factoring out the 2 like I did here, and then adding inside of it something that gets you like 9. Like we want s minus 9 in the numerator, right? And so in this case, you could add, so s plus 5 over 2 minus 23 over 2 plus 23. And this inside will get you 9, and then 23 you just work with it as a separate, fraction, and you do the inverse Laplace of that as well. But in our case, I just instantly kind of separated it. I'm like, okay, I want minus 9, so I'm going to subtract 9 and add 9, and I've done nothing differently. When I combine those two, it'll be 0. And my plus 9, I brought it over to here, so that's why I have this line. So I brought it over into this one. And so You'll know how I got 23 in a second. And so yeah, so I stated that like, okay, I have my s minus 9 plus 9, like I have my s over s squared plus 100 and my k over s squared. This should really be 10 right here. And the whole point of writing out these f1s and f2s is just to understand what formulas I can look at in regular form that aren't transformed on my formula sheet, because this s minus 9, as we all know, is a transform. It's really just s squared, but we have to take that into consideration. And so, yeah. So what ends up happening kind of after this point is you have s minus 9 plus 9, and I still haven't changed anything. In my case, when I bring out, the reason why this becomes 23, when I bring out this 9, right, I have to consider this 2. And so it's 18 plus 5. And that's how I get to 23 right here. And so now that we understand where we got the 23 from, we really want to focus what's going on here. Everything else up until this point has just kind of been preparing it for what we're about to do now. So I have my s minus 9 over s minus 9 squared plus 100. This is similar to the s over s squared plus 100, or plus k, really. S over s squared plus k squared is what I want to say. And we know based on our formula sheet it's cos, and the k value is just the square root of this, so 10. So that's fine right there. Now, you'll see that I haven't reflected the minus 9 here yet, and I do that down here. In my second kind of half, I have, my k over s squared plus k squared. And so because of that, I know that my numerator has to be, the square root of k squared. So I need 10 here, but I have 23. So I could factor out or divide. I'm really asking myself, what can I do, 23 over x equals 10, and what will that equal? What will x equal? And it equals 23, and so I know that 23 divided by 23 over 10 equals 10, and then I can use my regular sine function. So yeah, that's and then I reflect that in my final solution. This part you don't really have to worry about. I'm just explaining. Actually, I should go through it. So based on this function right here, hold on, give me 1 second, guys. I gotta. Actually, hold on. I think I should be fine. I just have family coming in, so I don't know if I'll have to stop it, but we'll see in a second. So yeah, so I'm gonna use this formula right here. It's in our slide deck, and it's basically telling us that the inverse Laplace of a function of s minus a equals e to the at, being the transform, and the inverse Laplace of the function. You're basically just kind of, I'm not going to go too much into theory. You guys know I don't like that, but just for the sake of what we're doing, applying it in theory is this right here. Applying it in practicality is that right there. So wherever you have an s, you're just plugging in s minus a. And because we get something like this, we know that our transform is 9, based on our previous question, right? And we just do e to the 9t times our initial f at s, and so combining everything together, this is my final solution. And I hope that makes sense. If it doesn't, I can try and explain it further, but for the most part, I hope that you guys understand practically what to do when you see something, and that's really what I want to get across. Because just understanding what to do when you see it is really all it is about the engineering as a whole. Okay, so we're moving on now to the fourth question. And fourth question, we see something nice in the denominator, something that'll get us a non-distinct real root. A non-distinct being it's just repeated. So we do our partial fraction decomposition. We get our a values, as we always do, and then we we take the transform of our new, partial, our decomposition fraction, so to say. And this we know. Now the second one, it's just 1 over s squared. And so we have n factorial over Sn plus 1. And from there, we still apply our transform of e to the 4t. Same thing here. But yeah, this time around we get a t attached to it. And I wrote down that formula right here. Okay, so moving on to the fifth question. We have, similar, we have an IVP, and we take the transform as we always should. I broke this part up in a left-hand side and a right-hand side case. So our left-hand side is nothing too crazy. We're doing sort of the similar kind of like steps, being that my y prime, where y double prime is reflected right here, y prime right here, and my y right here, and we multiply it by the corresponding coefficients. And yeah, so we're decreasing a term, multiplying by the initial condition, decreasing another term, and multiplying by the derivative of the initial condition. And we follow the same pattern here. And that's our left-hand side. Our right-hand side is this. We're taking the Laplace of it. So our f at t, kind of how our prof did, is that based on our formula of t to the n, we have f factorial over, I think in the initial question. Okay, yeah. So this is how it originally is. Because we have e to the 2 here, we have to reflect that and sub that in as s. But yeah, that's about all there is to that question. We sub everything back in, isolate for y at s, and that's the solution. Okay, so moving on to question number 6. Yeah, okay. Moving on to question number 6, we get, okay, I'm going to cut this part right here and start it out back in a second. So we have a general formula that kind of describes this question. And really all it is that when you see a Laplace transform, a Heaviside function, then you can associate g at t to your first, h at t to your second, and j at t to your third function, respectively. And then plug that in to the g at t. You're literally just doing the first plus the second minus the first times u at t minus a, plus the third minus the second times u at t minus b. And a and b being reflected here. So when you only have a 2-level Heaviside function, then I just say there's 2 levels to it, or 2 different functions. Then you only have a. When you get into 3, then you get b. When you get into 4, you'll get c. It's that's how it is. So the first one, we just plug it in. Our first function being 8, and then the following to that would be 1 minus 8, so we get -7. One really nice way to approach this question, like how our prof does, is just state 4 and then the interval. And then basically for u at t minus a or u at t minus 6, whatever it is, it's 1 for any value that's equal or greater to a, and 0 for any value that is less than a. And so we know that it's 1 in this case. And that's just like some preliminary knowledge that I want to give. To actually solve this question, you're just taking the Laplace of it. And, you factor the 8 out, you get over s. And then this part right here, you could use, which formula? Yeah, we're really using just this formula for it. So we're taking 1, so the Laplace of that, and then reflecting the transform in it off the t minus 6. And yeah, that's about that. Multiplying by 7, of course. And yeah, so that's that's the first part of that question. I started with the second one, but let me add another page and continue to go through it. Okay, cool. 1 second. Okay. Question number 6 right now. Okay. B. This is actually a question that I struggled with personally. For the life of me, I just kept doing what I was supposed to do from the lecture slides, and I couldn't actually get the correct answer. And so I turned to the internet, and the internet is a piece of shit. So I'm going to try and explain as best as I can how to approach this question. So we know that for B, right, we have really our f at t only equals t squared. So in our formula, because the second one would be plus 0 times, the rest of the shit. We'd have the second function minus the first function. Like it doesn't matter because we'll have, hold on, let me show you. So in this case, let me copy and paste it. Okay, so if this is what our function is, and copy and paste this as well. Don't let me copy and paste it. Oh, damn. Okay. I guess I can't just paste it, but that's fine. So our g at t is t squared. And then the second half of this will be, will be plus 0 minus t squared times u at t minus a. Okay, cool. So in this case, we have t squared minus t squared times u at t minus a. Okay, cool. And our a equals 2. So a equals 2. So I could get rid of this and just do that. Okay, cool. Now at this point, we got to take the Laplace of this. And, I'm just going to take the Laplace of f at t. Laplace of that. And we have t squared. So what I'm going to get is n, so 2 over n s to the n plus 1, so cubed. And now I have t squared. So my f at s will still be 2 over s cubed, right? My a equals 2. And so since I have to kind of like factor that in to my, like with the formula, I have to multiply it by e to the negative 2s when I'm done. And so this is, this question is where I completely like was getting lost when I was doing it. And even then, I'm going to show you how it's supposed to be done. But yeah, this question when I was doing was the C is actually a lot easier than this. So you'd think that by doing this, you're just going to do something like this. So like you're going to have t over s cubed times e to the negative 2s. And unfortunately, that's not it. When I was doing this question, I was like, why am I not getting the correct answer with B? Initially, I had just thought that it was just s cubed because of the 0. But no, that is not the case. For this question, the way it was solved in the online solution that I saw, you are basically doing something along this line. So all of what we're doing right now is based on like this fundamental theorem in our slide deck, which is that we have f at t, or I'll write it how he writes it. We have e to the negative st, or negative at, however you want to, and this is multiplied by f at t given whatever like boundaries you have. And in our case, we're integrating from 0 to 2. And with that, our u, so this is integration by parts, and I'll sub in the rest of my 0 to 2 e to the negative st times t squared. And now we see this is very clearly integration by parts. We have to set our u to t squared. Our du becomes 2t, and our v equals negative 1 over s e to the negative st, with our dv equaling e to the negative st. And I am not going to go through the full integral of this because I feel like it's a waste of time. You could search it up online. But the final solution ends up being 2 over s cubed. So the initial portion that we got right, minus 4s squared plus 4s plus 2 e to negative 2s over s cubed. And this was like that. This was the full solution that I entered into Child's Math. That was correct. C is a lot easier than this. And if anyone knows how to do 2b regularly, just let me know, because maybe it's this part that's confusing me. But yeah, this was about as close as to what I could get out of it. But yeah, you just have to literally compute the integral with your boundaries being like, I'll show you how mine was. This is how it was, b, and then this is the integral that I got as a result of it. But yeah, C is a lot easier. So C is f at t equals 0 cos 6 t minus pi over 4, and your boundaries are 0 is less than or equal to t is less than pi over 4, and t is greater or equal to pi over 4. So with this one, we're given very clearly that like so when we write our f at t, our first function g at t is 0, and then we're adding, our second function, cos 6t minus pi over 4, minus 0, and then multiply this by u at t minus pi over 4. And this all just equals you're going to end up having to take the transform of this, which is cos 6t minus pi over 4 times u at t minus 4. Okay, and this is perfect for our formula. Our formula being this one right here. So this is exactly what we wanted, and you could literally just like kind of plug it in. You know that your transform's negative pi over 4, and so you'll end up getting something along the lines of equaling e to the negative pi s over 4, and then because we have cos, we're gonna have to multiply by s over s squared, because of the 6 plus 36. And yeah, that's really about it. Our base formula is f at s equals cos of 6t, and then you're plugging in your t or your s minus a as t, and that's really all you end up getting. But yeah. Okay. Maybe I should explain it a little bit more. So I don't know what more there really is to explain though. You know that your f at s is just your regular f at s. So I'm taking literally the inverse, I'm taking the Laplace of this, which I know I'm going to get s over s squared plus 36 from. Nothing changes here. The transform is only being applied with the e to the negative, as, so to say. With it's really just you're looking at the transform, the inside of that bracket, and taking your a value and applying it to the as, e to the negative as. And yeah, you're just kind of using the form. Make sure you have these formulas on your formula sheet, and life will be a lot easier. Okay, number 7. I think you're at slide 9 of 4.4. When you see this interval, it should based on the question, of course, but generally they're gonna have to end up using convolution of two functions. We have a formula exactly for calculating f times g all at t, which you end up getting an integral like this. And so if we know that h at w at t is equivalent to that, then we can say, just kind of like subbing in our f at t and our g at t, that this is what we're gonna get. You really don't have to worry about this. You just gotta focus on this right here. And then yeah, you plug in this. Like you said, you can plug in this as your solution, or this. It just matters how much you want to simplify. Part B Part B and C can be used from slide 15 of 4.4. So I take my Laplace of both of these, okay? And now, because I want let me scroll down a little bit. Because I want the function that when I take the inverse Laplace, I can get f at g at t. Then my function will be f at s times g at s, based on this theorem, right? So whatever you have right here will be b, and then when you take the inverse Laplace of this based on partial fractions, you'll get c right here. And that's question number 7. Question number 8. I'm going through half the questions previously, hopefully with as much detail as I can, as you guys see fit. But question number 8, it's literally telling us what the solution to the convolution of two functions is. And so I actually really like this question. You can use this formula. This is literally just taking, if we go back here, if you take the Laplace of this, right, you'll cancel out this, and you'll be taking the Laplace of this. You'll realize that's exactly what I have right here. And you could apply linearity to this and expand it out, right, as we've done in previous formulas. And so based on convolution of two functions, I know that my f at t is this right here. My y at w would be like my g at t. Now my f at s is just the Laplace of that. And so I got my sine, I have my transform on the side. Just be careful that your w, it's asking you in the question when you plug in your answer to represent it symbolically as a function of s. And so you change your w to an s. And yeah, at this point, hold on, let me scroll down to number 8. Yeah. Okay. So then at this point, we scroll down a little bit. So I just got to make sure that everything I tell you guys is also in line with what the correct solution will be. Okay. So yeah, so I multiply my functions out. I know that my g at t is sine, my regular f at s is just sine of 6t. And so my Laplace is this. I can apply my linearity formula. And this is a continuation of g at t. And so kind of bringing everything together with the formula. That being this one right here, which where to go? Okay, so bringing everything together with this formula. Okay, so I know that the convolution equals 8t squared. It's given to me, 8t squared. And I want to solve for y at t. So, well, sorry, I want to solve for what I can take the Laplace of. So like the Laplace of y at t will equal my answer for a. So I'm solving for a right now. It should be clear of that. And so what I can do here, and let me represent this also symbolically to what I want. If my L at f times g at t equals L at f times s times g at s, right? And we know that this, okay. And we know that this is equal to my f at g at t, right? It's the same thing. Let me bring this down. Let me get rid of this. I should put this as clear as I can, because I know I'm wasting some of your guys' time. So if my formula is saying that this is equal to f. Oh, my pencil died. That's so dumb. Bruh, my pencil died. Okay, I wonder if I could just do this by hand. Hold on a second. No more pencil. I don't want a pencil. Okay. So we're going to do this by hand. So if my f at s times g at s, like I'm just restating the formula right now. And this formula right here, okay, will get me my convolution. And we have the solution to that, which is 8 at t squared. Then I can sub in, 8t squared right here, and then continue to kind of go about my problem. And so I'll show you that just in a second. I'm going to cut the video right here and wait until my pencil's charged and then continue back up. Okay, so Apple Pencil is charged. My bad. I think I got 2 cuts in this video so far. So kind of continue off where we left off. So then I could say that I got L at 8t squared. And if I know that, I also know f at s. So I only had, one function, which was this one right here, right? And I could say, the y at w, we don't know y at w in this case, but yeah. So I have my f at w equals y at w, and my g at t minus w equals sine of 6t minus w, and my f at g, like I wrote it down right here, is that. So if I take the Laplace of that, then I get 16 over s cubed. I already wrote it down here, but I just want to write it down again. And if I'm solving for, my L at g minus t, like I got this whole thing so far. I got f at s equals L of f at t, and my g at s equals L at g at t. If I plug everything together so far, then I will get this formula. I will get, my good ladies and gentlemen, 16 over s cubed equals f at s, which is sine squared, 6 over sine squared plus 36 times L at g at t. Multiplying up, I get L at g at t equals 16 times s squared plus 36 over, multiplying up and then down, over 6s cubed. Cool. So this is my answer to part A of the question. And just now, evaluating this is my answer for part B. And what I can do here is bring out the 16 over 6, have L inverse. So now if I take L inverse of L at g at t, okay, then I'll continue to go right here, s squared plus 36 over 6, over s cubed, okay? Then I will get equals g at t equals 8 over 3. This is just simplifying the 16 over 6. L inverse. If I break apart s squared over s cubed, I'll get 1 over s plus L inverse of 36 over s cubed. So the first part will be easy. It'll just be, L inverse of 1 over s is just 1. The second part, I can divide it by 2. So I get, because I have s cubed, which means I know I'm dealing with like t of n, and I need something factorial. So because it's because it's s cubed, I know I have 2 plus 1. So my n is 2. So I need 2 in the numerator, which means if I can factor out 18 and get 2, so I'll get 18 times L inverse of 2 over s cubed. So this equals 18 times t at n. And the 8 over 3, I also have to, expand it here. So times 8 over 3. And if you simplify everything, you'll get, or y at t, in my case, it's the g at t, plus 48 t squared. You could have subbed in y at t or g at, you could have subbed in either one of the two. You'll get the correct solution. You just have to understand what you're doing. Okay, so moving on to question number 9. I realize I'm gonna have to stitch the 3 videos together while I'm doing this, but it's fine. Okay, cool. So question number 9 is giving us a heaviside function represented in the graph. We could do this by kind of rewriting it as a heaviside. And so if you can read, I'm not going to go through explaining how to put this in its different form, but just kind of read what I'm writing down right now, and you'll be able to transfer that to the graph. So 0 is less than or t less than 1. We're up to 1 right here. And yeah, it's not inclusive, so you put the 0 at the end and just kind of go through it like that. And we're going to take it sort of, step by step. We're solving, our first thing is just entering the constants. And so I'm going to do the same thing as we did before. For 0 is less than or equal to t is less than 1. F at t equals a times u at t minus 1 plus b times u at t minus 6 plus c times u at t minus 7. And for this part, you guys really got to listen in to what I'm saying. Because 1 is exclusive, in the first one, I know that t minus 6 and t minus 7, u at t minus 6 and them both respectively, will be 0 instantly. And because my first one for that 1 is exclusive, it also equals 0. And so I basically get in my, oh, sorry, I wrote this down right here. It's not supposed to be there, that one. It should, yeah, okay. No, that's fine. Okay, so I wrote it down like how it should be. You can refer to the slides to see how I got this format exactly, but it's I think I also have to have a, yeah. So I have my 3. I went up to C in this case, and I know that because it's 0, I'll have U at t minus 1 equals 0 equals U at t minus 6 equals U at t minus 7. And remember that this is it with respect to my u's. My real function is f at t equals a plus b times u at t minus 6. T minus 1 plus c times u at t minus 6 plus d times u at t minus 7. Okay. Hold on. For the first one. Okay. No, I'm tripping. There's no d. I have the right formula there. So the first one equals 0. So f at t in my first sort of part equals 0, as we've written down right here. Gonna write that a little bit better. Equals 0. So I have nothing to gain from solving the first one, but at least it's good to know. For my second one, we have, and I'm kind of like transferring and transcribing as I rewrite my solution. When it's less than 6, okay, I know that u at t minus 6, it's not in the range, it's not equal or equivalent, but my 1 is now satisfied, right? And this is 1. My 1 is now satisfied. So now I have f at t equals 3. So I have 3 equals a and plus 0 if you want. But now we know what 3 equals. So I have my first term. Now in the second one, or third one in this case, for 6 is less than or equal to t is less than 7. I know that my 6 is now satisfied, my 7 is not, and f at t equals 5 in this case. So I have 5 equals 3 times 1 plus b times 1 plus 0. And so my b equals 2. Let me add another page. Continuing on, for t is greater or equal to 7, all of them are equal to 1, and my solution f at t is 0 at this point. So I have 0 equals 3 plus t plus c, 3 plus 2 plus c, and so my c equals -5. And respectively, my solution for a would be 3 to -5 after plugging it in. Let me grab my charger real quickly. Give me a sec. Let me write that down. Alright. Okay. I don't like to do cuts in my videos, but for this one I probably will have to. Just because it's so long and it's hard to get like a good couple hours, just pure silence. Okay, so that's question number 9. On to the last beautiful 6. Okay. So this question, I think, yeah, it took me a few tries. I think, yeah, I got it on my second try to get it completely correct. we're going to utilize this formula, and we're going to use a few actually. Okay, cool. In this case, we're asked to find the inverse Laplace transform of f at s, and so we're basically trying to find f at t. Oh, sorry, I'm down here. Oh, I think I went down too far. Yeah, there we go. Okay, so okay, so sorry, I was looking at the wrong question. Okay, so I want to find the Laplace transform of that. All I really need to do is expand it in. So f at t would then become 4 minus t times u at t minus 4 minus 4 minus t times u at t minus 4. Okay, cool. And now I'm taking the Laplace of this. So Laplace at f at t equals f at s, and so f at s equals the Laplace of 4 minus t times u at t minus 4 minus the Laplace of 4 minus t u times t, oh shit, u times t minus 4. Okay. Now, what we could do from here is utilize this formula. Where I ended up writing it down. Basically, all this formula kind of says is that L at, how did they put it? Hold up. I don't know. I forgot the formula, how it was exactly. It's in the slide decks. All you'll see in practicality is that I'm going to take whatever value I got right here. I'm going to take whatever value I got right here for my f at t times u at t minus a. And when I take the Laplace of this, it'll be Laplace of e to the negative at times the Laplace of f at t plus a. I think it's something along this lines. But basically you're just adding, I made that formula up just now just to see if it'll work out, but you're just adding whatever value that is, and you're keeping, this is like f at t is considered this whole part right here. I'm going to keep the 4, bring the e out with the a as the exponent, and then just add it, and then continue the Laplace like that. Okay. Let me see what else there is. Hold on 1 second, guys. Checking to make sure my solution that I wrote down here lines up with what I put in. Okay. Yeah. 7x. Okay, this is what I'm looking for. All right, so starting off, I get e to the negative 4s times L at 4 minus t plus 4. Okay, and then similarly, e to the 7, get rid of this. So 7 to the 7s times 4 minus t plus 7. Cool. And so this will cancel. I'm going to get e to the negative 4s times the Laplace. Could even bring the negative on the outside and just make that t minus e to the negative 7s times, this would be 11, or sorry, it's minus, so it'll be 4 minus 7, so negative 3 minus t. You could even, bring the bracket, bring the negative on the outside and just make that positive, so e to negative 7s times 3 plus t, or the Laplace, let me write that down, times the Laplace of 3 plus t. So my left one will be negative 4s times 1 over s squared. Okay. And then my second one will be e to negative 7s times 3 over s plus 1 over s squared. And if you enter that, you'll be just fine. Cool. I think that's about it. Yeah. Okay. So now let's move on to the 12th. Oh, no, we're moving on to 11th question. Just got to make sure I put it in here right. Okay, cool. So, enter the function. Okay, so I know I can't like do the, so I'm looking for the inverse Laplace of this, right? And in this case, I could see, something pretty clearly. Let's look at this a little bit more. My handwriting dropped off so much. So I have f at s equals e to the negative 4s times 6 over s squared plus 36. It's very easy to see that this is a transform. And this part right here becomes sine. As if I refer back to my sheet, yeah, sine is the one that just has the k up top. So what I'll get is sine, but I need to apply that transform. So I'll get sine of 6t, right, times the inverse Laplace. I shouldn't do those separately. Sine of 6t, but I have to consider the transform of negative 4. So I have sine of 6t minus 4. And that's it basically being represented in the form of g at t times u at h minus t. If anything, you could actually, because that it's going to go into this form, you could say that you'll have, actually we did a problem earlier like this. You'll have sine 6t minus 4 times u at t minus 4. There you go. And yeah, we did, this is based off of like the e to the negative as times f at s equals f at t minus a times u at t minus a. I think it was like something like that. In this case, the inverse Laplace. Yeah, okay. I think I just kind of wrote this off memory, but I think that's how it applies. Because if I take the inverse Laplace of this, then I'm going to get the inside of that, which is what I'm looking for. Okay, cool. This question was not so bad. So my inside in this case, so my actual function g at t is sine of 6t minus 4. And then my inside would be t minus 4. Okay. Moving on to number 12. Similar question this time around, but I'm going to end up having to do either like well, I can't do partial fractions because this can't be factored. I'll write it down like this. Factored, because you'll get imaginary roots. On the other hand, I can split it apart. So what I could do here is do like e to the negative 7 to negative 2s okay. So this is what you know I have when I fully expand it out, and if I take the inverse Laplace of this whole thing, the 7 I would have to bring out, right? And then I'm just looking for I just have s over s squared, so I know I'm going to get cos. So cos of t, it would be cos of 3t minus 2 minus sine 3t minus 2. And yeah, that looks about right. And then the inside of both of those functions, you could factor out. Actually, no, you can't factor out anything here. But the inside of both of those functions in this case would be t minus 2. And that's what they're looking for. Okay, cool. If I remember correctly, this question right here was a pain in the ass. Just a lot of work. Yeah, it was like 2 pages of work. I bet if I'm getting a little bit tired. I like to talk about math, but not for this long. Okay, so find the Laplace transform of the right-hand side of the above differential equation. And we could do that no problem. Let me just check how much battery I got on my laptop. Oh my god, I got 8%. Okay, hold up. 1 sec. Alright, so find the Laplace transform of the right-hand side of the above differential equation. The right-hand side, if I want the Laplace transform of the right-hand side, I could also just do the Laplace transform of the left-hand side because they're equivalent. So I really just want to say I'm going to do this and you figure it out. But so if my left-hand side is y prime plus 5y, and I want the Laplace of this, then I'll get s times y at s minus y at 0. And then plus 5 times y at s. Factor this out, and in my case, so the right hand side, so I got the left hand side right now, right? And hold on. Want the right hand side and the left hand side. So in this case, what I can do here, instead of fully doing the left hand side, actually wait, hold on. Instead of the right hand side, why am I doing the left hand side? Okay, hold on. Scratch that, guys. I'll probably end up cutting that out, just going straight to the right hand side, or not. So right hand side, to make that, I want f at t equals 0 plus the second, so 10 minus 0 times u at t minus 1, and then plus 0 minus 10 times u at t minus 7. So if we expand everything out and factor, we'll get 10 times u at t minus 1 minus u at t minus 7, and take the Laplace of this, and you will get 10 over s times e to the negative s minus 10 over s times e to the negative 7s. You guys know how to do it at this point. Just imagine you got a 1 right here on both of these. Okay. Then the second part of it asks, let y at t denote the solution to the above differential equation, and let y at s denote the Laplace transform of y at t. So find y at s. So they're basically telling us, find the Laplace transform of the left-hand side, which we could do by all means. In this case, similar to how I was mixing up b and a. Yeah, my bad, guys. I was mixing up b and a. So if y at t equals y prime plus 5y, and y at s equals the Laplace of y prime plus 5y, which is y at t, then this equals s times y at s minus y at 0 plus 5 times y at s. Now, in this case, we will have 0 equals y at s, or sorry, Laplace of y at s equals that. And we'll have, after we factor out, we'll get y at s times s plus 5 minus 9. Now, because I took the Laplace of the right-hand side first, and I'm taking the Laplace of the left-hand side right now, I could set them equal to each other and solve. Over se to the s minus 10 over se to the 7s, and solve for y at s. And so y at s equals 10 over se to the s minus 10 over se to the 7s plus 9 times s plus 5. Cool. Now they asked me, by taking the inverse Laplace of your answer to b, the solution y at t can be written in the form blah 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 blah, and then enter everything else accordingly. So if I want the inverse, of this, then what I could do is so I'd probably expand it in first. 10 over e to negative s plus 5 minus 10e to negative 2s over, or sorry, it's not negative 2. Negative 7s over s plus 5 plus 9 over s plus 5. And then you're going to take this and do partial fraction decomposition, and you'll get 1 over s plus 5 equals a over s plus b over s plus 5, and 1 equals a s plus 5. Actually, I'm not going to solve for it again because you guys know how to do partial fractions. In the end, you'll get a equals b equals, so this equals 1 over 5, and this equals negative 1 over 5, and then I end up subbing everything in, and so I'll get 10 over 5s e to the negative s minus 10 e to the negative s over 5 s plus 5 minus 10 e to the negative 7s over 5s plus 10e to the negative 7s over s plus 5. You can see how the decomposition kind of went about now, times 9e to the negative 5s. We take the inverse Laplace of all of this, and we get 2 times u at t minus 1 minus 2 times e to the negative 5, u at t minus 1 minus 2 times u at t minus 7, plus 2 times e to the negative 5, u at t minus 7 plus 9 over s minus 5. And you're looking for this as your answer to you're looking for this as your answer to part E. And for part D, when you factor out u at t minus 1, at least it was for me, f at t is what I'm looking to enter. So I'm looking to enter for part D, negative 2 plus 2e to negative 5 t minus 7, and for E, 9e to negative 5t, because you're literally just looking for where you had s and plugging in t. I work with different variables, but that's fine. Let me see what else I got here. So wait, yeah, no, I got that. Actually, it doesn't make sense. Doesn't make sense how I just did partial fractions and then I got that. See guys, this is what happens when you copy off of the wrong fucking sheet. Okay, so what I'm gonna do here is I'm gonna apologize for wasting your time on this one, on this part right here. And I'm going to sub in what I have written on literally the page right after it. Because like sometimes I'll read through my solution sheet and then I realize, hey, this wasn't a solution sheet. This is one of the tries that you put in that you got wrong. But okay, so I think up to here I'm still good. Let me check. So I have 9 s plus 5. Okay, yeah. So I'm cool up to here. When I go to take the inverse Laplace right here, I get, e to negative s. I shouldn't factor. I should keep that in there. So I have to take the inverse Laplace of everything in there. I know I'm gonna have to take partial fractions for these two, and when I go to do that, I end up getting a equals 2 and b equals negative 2. Now after I do that, I get e to the negative s times the inverse of 2 over s minus 2 over s plus 5 minus e to negative 7s times inverse of negative 2 over s. Sorry. Oh yeah, they can't be the same. This is negative. 2 over s plus 2 over s plus 5 plus 9e to negative 5t. There you go. And then since we have the e to negative s on the outside, we make this u at t minus 1 times t minus 2 e to the negative 5. Make sure you sub it back in. And close this off. Then we have negative u at t minus 7 times negative 2 plus 2e to negative 5 t minus 1. And there you go. That is your answer. And then that's how I got these two. Okay, cool. that was one of the larger questions that I did not like. So if you guys want some review on that, just reach out to me and I will try and walk you through it. But for now, I think this is close to like a streamlined answer that I can give you. Just mind the hiccups. The people who really want to know will stick through me on that end. But I eventually get you to the right answer. Okay, cool. So this is 14. I have f at t, writing this as a heaviside function. I'll get 0 for 0 is less than 2 is less than t. 2 at t minus 2 is 2 is less than or equal to t, less than or equal to 4, because it's inclusive. 4 and 4 is less than t is less than 9, and 0 is t squared equal to 9. And so I'm looking to, what am I looking to do this question? Find the Laplace transform. So really all I need to do here is just kind of go f at t equals, so the first one is 0, so I don't even have to write that. Starting with the second one, 2 at t minus 2 times u at t minus 2 plus 4 minus 2t minus 4, expanding that out, times u at t minus 4 plus 0 minus 4 times u at t minus 9. And then after I've expanded everything out, I'm going to simplify it. So I get 2t minus 2 times u at t minus 2. This is nice because I can just use my formula, times e to the negative 2s times 1 over s squared. And then continuing on, minus 2e to the negative 4s times the Laplace of t plus 4 minus 4e to the negative 9s over s. And this second one, we get 2e to negative 4s times 1 over s squared plus 4 over s. And this gets brought down. And that is correct. I just want to make sure I'm right here. Hold on a second. Yeah, 14. 2s. I get 8 from in the first one. Hold on. Did I expand? Oh, this is supposed to be plus. Shit. Okay, yeah, 4. Okay, yeah, so the first one's right. This one's correct. Then we have minus 2e to the negative 4s over just s squared. There's no 4s. Oh, yeah, these cancel out. Yeah. Okay, yeah, that cancels out. You just get negative 2t. So you just have this. So your final one will be negative 2e to negative 2s over s squared minus 2e to negative 4s over s squared minus 4e to negative 9s over s. And this is correct. Okay, cool. So moving on to question number 15, and the second last one. This question was actually quite nice, and it's nice because it's simple. So we can write this, expressing this in terms of a regular equation, a at t plus b at t minus a at t times u at t minus 2 plus c at t minus b at t times u at t minus 6. And then we will just expand it out. We know that f at t equals this. So expanding and simplifying, we're going to get a at t plus b at t times u at t minus 2 minus a at t times u at t minus 2 plus c at t times u at t minus 6 minus b at t times u at t minus 6, and then isolating and everything, plus b at t times u at t minus 2 minus u at t minus 6 minus a at t times u at t minus 2. The reason why I don't have to isolate for any of these is because in my initial equation, right, in f at t, I only have u at t minus 6. There's nothing else I could factor out other than b at t to get that, which means a at t and c at t must both be 0. And so what I plug into my box on 15 for a is 0, 2 times t, and 0. And then b, I literally just plug in. I see where, like what they asked me for evaluate f at 4. And so I know that 4 will lead me to be in just, It'll lead me to be just in this interval. And so since I'm just subbing it in for bt, and b at t equals 2t, and they want 4 times 2, I just get 8, and that's my solution for 15b. Now last, and thank God least, because I love math, guys, but this assignment with the breaks and like how non-smooth some of the questions went. Last but definitely least, number 16. And yeah, this is another one of those just kind of like Laplace and then simplify. We are looking to find the left-hand side and then the right-hand side. This is Dirac delta, and you could find this on slide 3, literally. You could find it on slide 3 of like 4.5, I think. Yeah, 4.5. So that's how I solved this question. So left-hand side is as usual. Thank God we have these nice initial conditions. So I'm just going to get straight to what I need to do, which is y at s squared minus 4s minus 12 equals the left-hand side. Since I have s at t minus 8, it equals e to the negative 8s. And so y at s equals e to the negative 8s over s squared minus 4s minus 12. And we haven't gotten anywhere with the question just yet, but since we're asked to sort of like get it in the u at g at t, and h at t, I know that I'm going to have to do an inverse Laplace here. And so to do that, I factor out, not really factor out, but I just kind of manipulate it such in a way that I get my correct denominator. Gonna do partial fractions, get a equals negative 1 over 8, and b equals 1 over 8. And now taking the inverse Laplace of this whole part, okay, then I finally get u at t minus 8 times negative 1 over 8 e to negative 2t plus 1 over 8 e to the negative 6t. And that's about it. This is my answer for B, and this is my answer for A. So thank you. for listening/watching. It's been a pleasure helping you guys with this class. I know I didn't get like much feedback throughout the videos, but if you guys have like anything, any recommendations, any suggestions, maybe new courses to cover, I want to take some time to elaborate a little bit on my specialization, as I've heard many people asking. Basically, I'm tentatively between software or civil engineering, and I really, after like my analysis, I want to work in the Emirates, and one of the largest types of in-demand engineering will be civil. But at the same time, I love software, and I think that that's really where the future kind of will tend to lead to. And so I don't plan on stopping to do software related videos. I will probably have more math related videos towards civil engineering, and I may introduce someone to make videos on discrete math, and maybe I just might fuck around and make a video series on data structures and algorithms, but who knows? We'll get to there when we get there. But I don't plan on stopping to make these videos anytime soon, and yeah. So I hope that kind of answers some questions. I'm on a wait list as it stands, and I'll know in August on what stream I get placed into. So we'll see what happens with that. For anyone that's listening or has made it far into this video, thank you, and I hope that you have the best of luck following Math 2Z03, and that I will share many more classes with you guys in the future. But thank you so much for watching, and I will see you in the next one.